Clustering. So it's been quite some time since we started. So let me go back to an older slide to tell you when you use clustering. You can see here that when there is a target variable to be predicted, we choose classification or regression. Hence, they are called supervised learning models because you provide a target value which the model has to learn to associate with the input data. There could be cases when there is nothing to predict. You just have a set of variables and their corresponding values for multiple observations. You are just interested to know if there are any patterns or groups or clusters in the data. So this technique is called clustering. It is an unsupervised machine learning algorithm. You can take a look at this for some further information about clustering. So clustering is an unsupervised machine learning task which divides the data into multiple clusters. It is used for knowledge discovery and not for prediction. It provides an insight on natural grouping found within the data. Clustering is guided by the principle that items inside a cluster are similar to one another and different from those outside. Meaning, when your data has three clusters, say A, B, and C, the data within cluster A are identical to one another, while the data in cluster A is quite different from the data in cluster B. K means clustering is the most common clustering method. So here the data is split into K clusters. K is a number which has to be decided in advance by the user. It is quite similar to the K-means algorithm used for classification. Now let me give you an example. You have a data set of 1000 cricket players with their batting average and bowling average. Again, for the uninitiated in cricket, batting average is the average number of runs scored by a batsman in one match, while bowling average is the number of runs conceded by a bowler before he takes a wicket. So it should be obvious that higher the batting average, better the batsman, and lower the bowling average, better the bowler. Now, if you have the data for bowling and batting averages for 1000 players, you may find three kinds of players in this data. Cluster 1, players with high batting average and high bowling average. These are proper batsmen who are not very good in bowling. Remember, lower the bowling average, better is the bowler. So in this case, we have a player with high batting average and high bowling average, meaning he is a very good batsman but a poor bowler. So let's name this cluster as a pure batsman. Next cluster, players with low batting average and low bowling average. So these are proper bowlers who are not very good in batting. So let's name this cluster as pure bowlers. Cluster 3, players with high batting average and low bowling average. These are players who are good at both batting and bowling. We'll call them all-rounders. So I am assuming there are no players with low batting average and high bowling average. That is, who do neither batting or bowling well. So now, since we have given the cluster count as 3, we have been able to segregate the data into 3 kinds or 3 clusters: pure bowlers, pure batsmen, and all-rounders. So suppose I had given the cluster count as 4. We could have got another cluster depending on the data. So this could be players with fairly high batting average and high bowling average, and one more with extremely high batting average and high bowling average. So the first one I'll name as good batsman, and second one I'll name as great batsman. So in addition, I have already pure bowlers and all-rounders. Now 4 clusters: pure bowlers, all-rounders, good batsman, great batsman. So it could as well be that bowlers could have been divided into 2 clusters as good and great bowler, if that is what your data holds. If we had given 5 clusters, probably we could have this case as well. Or maybe the batsman could have been divided into 3 clusters. Say we could have got average batsman, good batsman, and great batsman. So how do I choose what value of K I should give? That is, how do I guess how many clusters are there in the data? So let us first understand how the choice of K impacts the clustering model. So when the value of K is very high, say it is almost close to the number of records in the data set, almost every point is assigned to a unique cluster. So this means members within a cluster become more similar to one another. Say if a cluster has only 3 records, the members, these three are very similar to one another, but they will be less distinct from the neighboring cluster. That is, there may be no clear distinguishing characteristic between the clusters. Say for example, I will say we'll pass k equal to 12. So 12 clusters in our data. So how it could split as batsmen with average 20 to 30 in one cluster, 30 to 40 in another cluster, 40 to 50 in next cluster, 50 to 60 in another cluster, etc. So all batsmen in cluster 1 have a batting average of 20 to 30. So this is more specific than our earlier clustering where we just said good batsmen. But what is the difference between cluster A and cluster B? Cluster A has a batsman with average 28. Cluster B has a batsman with average 32. There isn't much to pick between the two batsmen, but still we put them in different clusters. So it is difficult to infer or label these clusters. On the other hand, with a lesser number of clusters, we said cluster A comprises of good batsmen, cluster B comprises of great batsmen. There is a clear distinction between these two clusters. Now, if we choose a very low value of k, no meaningful patterns can be spotted. So our value of k should be an ideal value between these two extremes. A scree plot is used to identify the number of optimal clusters. The scree plot provides a plot of the number of clusters against the within cluster sum of squares of distances. You really need not to worry too much about how to calculate and plot it. So R and Python generally provide packages to generate scree plot. But it is always better to use your business judgment to determine the optimal number of clusters and also see if you can label the clusters generated. Okay, this is a sample scree plot. Generally, when the number of clusters increases, the within cluster scatter decreases. At some point in the plot, there will be a sharp bend. This point usually denotes the ideal number of clusters, which indicates that beyond this point, there is not much benefit in adding new clusters. 4 is probably the ideal number of clusters based on this graph. You could try out 5 as well to see if you are able to interpret the results and label the clusters. You can see that scatter for 6, 7, 8, 9 are almost equal. So beyond 5 clusters, there is absolutely no point in adding more clusters. Let us see how k-means algorithm works. Consider a data set with 2 clusters. So the algorithm will start by guessing the central points of each cluster. Let's call them pseudo centers. And then it will assign each data point to the nearest pseudo center. Then the location of the pseudo center will be updated to the center of the respective clusters. These 2 steps will be repeated until there is no changes to the cluster membership. K-means clustering works best for spherical non-overlapping clusters. That is, algorithm divides the data into spherical clusters. You cannot have elliptical or square clusters, etc. These are some applications of clustering. You can do customer segmentation based on demographics or buying patterns. You can detect anomalous behavior like unauthorized network intrusions or fraudulent banking transactions, etc. In the next video, we'll perform a hands-on.